Yeah, so the second lecture of mine, we talk about this topic, which is entrant scalability. And the majority of the entrant scalability, I think all the entrant scalability happening on layer one. Because when we see entrant, it means the data and transaction happening on layer one. That's why we call it entrant scalability. And for this entrant scalability, for today's session, we're only going to talk about the computation scale. And there are two things we're going to cover. One is transaction and data sharding. The other one is blockchain interoperability. It's two different vertical in terms of how you can scale on layer one. Today's session may be a little bit heavy. I hope you can follow with me, even though it's on a Saturday evening. Yeah, so this is what we're gonna talk about today. So for as we discussed last sector, we talk about the issues for blockchain scalability, where in essence for the earlier blockchains like Bitcoin, Ethereum, by right, every node should process all the transactions and store all the data, also all the transactions or the ordering should be taken account on every node. So that's in general how it works. But when we want to scale, right, a typical reasoning after this is like, what if we split the transaction processing into a smaller group, like what you see here, right? So this is a typical non-sharding blockchain. If we shard this blockchain into two pieces, and this shard A only handle certain amount of workload, shard B also handle only a certain amount of workload. By right, we are able to achieve parallel computation in terms of the scaling of that initial blockchain, right? So that's definitely the fundamental idea on the sharding for on-chain scalability. So as I mentioned, by partitioning into two parts, we are able to horizontally scale the blockchain. So some people also call it a scale out, other than horizontal scale. So the transaction processing will be processed into multiple shards. In this chart, it's only two shards, but in reality, later on, we're also going to talk about there are multiple shards. But the more shard it has, the more difficult it will be for making sure the integrity of all the transactioning. So on a typical example, I like to use database, for example, to give you an idea of blockchain, because on the essence, because I did database before, on the essence, it's actually very similar. If you think about these two domains of data storing. So for a typical database, especially the popular ones like MongoDB, if the workload comes to almost 1 terabyte data, in order to help the computation and also data retrieval and data storage more efficient, MongoDB split into multiple shards. In this example, we split into 4 shards, and each shard only handle a certain amount of data, right? So the reason being is like, as I mentioned last week, or last session, is because each node can only handle a certain amount of transaction due to the hardware limitation. But definitely you can increase the hardware limitation by having more expensive CPU, GPU, and memories, bigger memories. but there's a limit, right? That's why MongoDB split with sharding. So by sharding, what MongoDB can do is, if it's a high throughput read and write request load, for example, if you see here, right, I can do the read and write to these two, but what if I have another concurrent read and write? The data only stored in this shard A. So then the shard B will be spared, and the shard A will take the workload. So if there are other concurrent read and write happening for shard B, the shard B can actually handle more workload from shard B. So that's where we get a better parallelization and higher throughput. Also, right, by doing this, the search can be smaller because the router, imagine a router for MongoDB is like a load balancer for web service. By doing that, right, I can use an index table to index the data I want to read and write into certain smaller shard. By doing that, definitely will have a faster response time other than search a whole database with 1 terabyte data. So that's traditionally how database has been doing. Absolutely, as I mentioned, in order to do the index, there's a terminology called shard key, where that's an index field to index all the data in the different shard in the router, so that the router can decide which piece of the shard should this request direct to. So again, right, the shard key normally has a range. So this is, again, easier for the data to be retrieved. So here, for example, we have a minimum key from, I don't know, maybe 0 to 75, then minus 75, from the minimum key to minus 75 to 25 and more. So by doing this, right, we are able to basically index all the keys into different chunk of data into different shards. So this is a little bit more complicated database. On the left side is actually a Google spanner. I highly recommend you read this paper here. This is kind of, to me, a revolutionary for database, because a lot of people, last session we mentioned, the cap theory cannot be resolved. Actually, with this architecture proposed by Google, they in a way solve the issue of cap, and a lot of Google sometimes mention they are a cap database, but there's actually a trade-off. Just briefly talk about this, right? I don't want to take too much of time. So on the high level, the reason initially they designed this because Google Cloud, as you know, is a multiple region cloud services, right? There are companies like Uber, like Airbnb, they have customers across the globe. And in general, the users in Asia do not access the data in Europe for Uber. For Airbnb, it's another story. But when this is happening, right, the users in Asia definitely should visit the data stored in Asia. So that's where they break down the data into multiple zones. Imagine this is more like Asia, US, and Europe, kind of a different zone. So in each zone, this is not shard. This is more like partitioning of the network, so that the Asia people can just access the Asia database. So inside of this partitioning, they have this called placement driver, which basically sorts the data. When the Asia people access the Uber data, they will actually store the data in Asia partitioning. And underneath this Asia partitioning, they have the participant leader of the data. Anytime the user's data want to store, the basically, in order to achieve the, remember CAP, right? Consistency is a big thing. Availability is another big thing. To make sure the consistency and availability issue to be resolved, we actually have a 3 replica in each data center zone. Sometimes people call it AZ, right? Availability zone. Where these 3 replica make sure the data is always available, because the chances of all these 3 replica is down is very minimum, because they will use multiple data centers, as you can see here, to make sure the data center won't be down. Well, it happened only once throughout my career, like the whole Asia data center was down for Google. But in general, that don't happen that often. To achieve 99.59% of the availability, these pretty much can serve the purpose of the quality of the service. In order to make sure the data is synchronized among these replicas, again, you see they are using Paxos. It's one of the typical consensus algorithm for database to make sure anytime they store the data, they do the 2 phases commit. So I commit, the first time I commit, I store the data, for example, in this replica, and only throughout this Paxos consensus algorithm, I make sure all the replica receive the same amount of data. I do the second phase commit. So that's where I can achieve the consistency too throughout this architecture. Yeah, so what will be the issue for this? With this architecture, it seems revolutionary. Anyone can think about an issue for this kind of solution solving the issues. Anyone? No? Any idea? I give you a tip. As a boss, I want to know what's happening for Uber in Asia or cross globe. Do you think the boss can, or the engineer, data engineer can quickly retrieve the analytical information from this kind of architecture? Yeah, the answer is like, to do analytical analysis, this kind of architecture is a big issue. So that's where PinCap, the TIDB I used to work for, invented this solution where I also do this similar kind of sharding methodology, refer heavily on the Google Spanner paper. They actually, when they store the data onto the disk, they also doing this one. Basically, they transfer a row-based database to a column-based database. So it's like this, right? If I do a row-based database, I know a person called Alice and his age and all his information, I can retrieve it. But imagine I store all the data like globally into multiple zones. And I want to know for a person age at 28 and female, when will he or she take the taxi the most, during which time? So this kind of information, you can't get it from a row-based. You can get it from row-based database, but in order to analyze, it's a lot of work. So in general, people, I'm not sure whether you guys encountered this issue before, but anytime you want to retrieve account information in a big bank, sometimes they tell you I can't because they are doing data batching during nighttime. The things they are doing is basically try to gather all the information into an analytical database, and doing it after our working hours. It's a lot of work. That's where by TiDB, by doing this, right, we also able to achieve analytical analysis immediately. So that's where we call it a real-time HTAP kind of database. So the reason I explain you is like the more you dig into the blockchain, the more you realize a lot of ideas are from traditional database. And if you, in the future, you are stuck on the research, on the study, on the work, always come back to the thesis and the basics. It's always the same, right? So we talk a lot about the traditional database, but the traditional database is very different still with blockchains, right? On one hand, it's a trusted infrastructure. What does that mean? That means like you trust Grab, host your data safely, and the other ones like handling all the data safely. You trust them, right? On the other hand, it crash failure, because with the replica I just mentioned, anytime the data crash, there's always a replica available to handle the data. And also it's a permissioned identity, because I always know who is the one trying to access the database multiple times. Since fraudulent behavior during a certain time, I can always block that person. That's a very typical features or things for traditional database sharding. On the other hand, the blockchain is different. It's very different. Where it's an adversarial network. What does this mean? This means like anyone, good or bad person, can be part of the network. You don't know who they are, right? And also it's a Byzantine failure, which means there's maybe data loss, there's people trying to hack the systems. It will always happen. The node also crash. And also there's a chance people doing a single identity, which means they create a million account, and you may not know who they are, right? This is very different to the blockchain from this perspective. That's where, when we talk about finally blockchain sharding, we have to handle all these issues, because traditionally, since all the database has been resolved these issues already, but for blockchain sharding, we have to handle all these issues. And very initial version of the sharding is a solution called strawman sharding. So basically, each shard has their own validator and manage their chain separately. What does that mean? So this chart shows you a little bit more clear. So these are multiple validators, because for sharding, other than mining node, we also have a validation node. The validation node is make sure any block insert into the blockchain is valid. So who is doing the validating? This is basically the validator. So I pause here a little bit. Have you heard of this before? On your previous class? So that I don't. Okay, cool. I just want to make sure, because I'm not synchronized with other teachers. Yeah, so the idea is, for strawman, I can shard this blockchain into multiple blockchains. Remember what we just talked about, the database, right? So for this shard, for this blockchain, for example, if you want to hack the system during the attack, you have to take 51% of the validators to basically tell the blockchain the next block is valid, right? If you want to hack it, take a lot of resources to hack those validators. Or imagine I basically fake my identity, become one of the big validator providers. But if you shard and you split the validator evenly, so for example, this shard, there's only 3 validators now. So compared to this and this side of sharding and validation is much easier to hack, because I just need 2 validators now to hack this blockchain. And I can generate a new block, and then the others will follow to generate a new block. So that's the problem, right? So these heavily reduce the security of the shard chain. And basically, the current assumption for the strawman solution is the validators are pre-assigned. It's not randomly assigned. That's where if you know who are the validators or where can I be the validators in which shard blockchain, I can hack it easily. And also you can't, with these solutions, the simple solutions of strawman sharding, they didn't really provide a solution. For example, if the user A on this block, and I want to send the transaction or transfer money to B on another shard blockchain, I can't do it with such strawman shard solutions. The solutions is easy. As I mentioned, like we can provide a random assignment of the validators to the different shard as a validators. So what's the difference? This calculation for a random assigned validators, please follow with me. So, so assume these are all the validators on the pre-sharded blockchain. We have like a P1% of malicious validators. Let's assume the P1 is 30%. 30% of the validators are malicious node. They can potentially hack the systems. So they will be randomly allocated to the different shard on the sharded blockchain. So let's say this is a P2% of the malicious validator node. So let's assume there's 100 validators on this side, and we have about 10 shards, which means each shard we will have 10 validators on the sharded blockchains. So by doing this, right, we want to know, by doing this randomly assigned validators, whether it's more secure compared to strawman solutions. So that's where I did a simple calculation where I want to know for P2 whether the possibilities of P2 more than 30%. Why 30% is here, right? If it's more than 30%, basically the possibility of that will become a hack for one of the shards, right? So to do that is actually, again, not that difficult considering your background. So this is how I calculate. This is how I calculated. So basically, it will equals to the ones who are the probabilities for the P2 less than 30% of the validation node, right? So this is simple. And then because I assume there are 10 validators on each shard, let's calculate the chances for the P2 malicious node to be less than 30%. And we just basically select from 0 to 3 on each, for example, on each sharded blockchain, the chances for the malicious node to be 0, to be 1, to be 2, to be 3, and add them together. This is the ones we calculate, right? And the result is 35%. So what does that mean? So the chances for P2 to be malicious, which is more than 30% of those malicious validators on one of the shard, is 35%. So think about just now the ones we had an example here. If you calculate this one, the chances for the strawman sharded got hacked is about 5.1%, right? It's here. So this result is definitely better than the strawman solution. I think it's apparent, but I just want to walk you through how we get it. Any questions so far? Okay. Yeah, go ahead. Yeah, you are right. So, yeah, you are right. So this solution is assume it's pre-randomly assigned. It's not dynamically random assigned. Yeah, so that's where I talk about the solution for the issue for these solutions. The good part for the solution is it's a little bit more secure, right? Compared to the 5.1% we got now, 35% more secure. But the issue is it's still a smaller target right now. So it can be compromised with after you know, because once you know who are pre-randomly assigned for that shard, you are still able to fit that sharded chain by fit the validators in those shards, right? So that's basically what you were asking, right? Yeah. So again, this is not a perfect issue. I want to walk you throughout the industry how they finally come out with the final solutions. Just bear with me. The solution for this is, as you mentioned, we need to randomly shuffle the data and even rotate the validators occasionally, so that the malicious node operators don't know who are the sharded chain has more issues for that validators. If we want to do that, we need another chain on top, which we call a beacon chain. Right? Does it answer your question? Yeah, cool. Yeah, so bear with me for that chart. We won't talk about now. But again, how we get a really unbiased randomness, right? So in the industry, we got a typical two solutions. One is called RANHOOD, which is a large-scale distributed protocols where it provides a publicly verifiable, and predictable, and biasable randomness against Byzantine adversaries. I won't go into the detail. We have a paper here talk about this solution in more details. This is a very interesting one to really get an unbiased randomness. Another solution we hear more is called verifiable random functions. So how do we achieve that? Basically, we have the public key here and also a private key here. Once we hash those keys, we get a random number, which can be verified. This is a fully randomized number after this function has been calculated. So this has been, I think, proposed by Vitalik, has been utilized a lot into multiple blockchains. We can also talk about this, how we use the random algorithm later during the next few sections. Yeah, so how to really facilitate cross-shard transactions, as I mentioned. So one of the issues for strawman and another improvement after that, we talk about we still cannot do cross-shard, which means as a user from here in this shard, I want to transfer the money to another shard for another user in the other shard. And these are a typical beacon chain architecture, simplified one. We call it a hub-spoke architecture. So why by doing this we can really provide the cross-shard transactions? It's because as a beacon chain, the beacon chain will have an updated state on that beacon chain. And on that beacon chain, we also have a validators on each shard, where each shard periodically they will send or commit the new blocks into different shard here, right? So the shard will be calculated. Some of them will send the full block of the transactions into the beacon chain. Some of them only send the headers of the block into the beacon chain. So basically, by doing this, we have different protocols we're gonna discuss later. And so from the shard to the beacon chain, there's a terminology called chain link. It's not that chain link, it's this chain link as a term to basically transfer the data in between, right? So as I just mentioned, we need to decide, shall we transfer the whole data to the beacon chain or only partially, right? And also, when we use this architecture to do the cross-shard transactions, how can we validate and process the validation and the data updated into different sharded block, and also in a beacon chain or shard chain, whether we should store all the data in beacon chain or only partially, right? So these are some of the questions when different protocols implement cross-shard transactions, very typical one. So as I mentioned, the chain link is basically the data transfer in between the shard blockchain and the beacon chain. And sometimes they transfer the entire block, which we call it, which is only the transaction sharding only for this entire block. It's not the data. So where the global state in the beacon chain, the cross-shard transaction, it's a synchronized execute in the beacon chain, because for the beacon chain here, right, I get the whole block from all the sharded blockchain. Now I can immediately calculate the global state on the beacon chain, right? If I do entire block commit. But if the chain link only commit to the block header, we will only commit to the state sharding, and also some of the transaction state sharding only to the beacon chain. So there's an issue for that, because when you do that, the beacon chain won't be able to validate the whole entire block, whether the previous block and the current block, especially the current block, is validated. It's all because they don't have a global state by doing this, because they only have the header information. They don't have the whole block information to recalculate again. So that's where think about the two phases commit for the database we just mentioned. So it's a similar situation, right? We need to make sure when the users A send the money to users B, I need to validate whether this data is valid on these two blockchain through the beacon chain. And I, as a beacon chain, I can't immediately validate the current transaction is valid until I get a commit from both parties. The data or the balance has been updated. Any question? I know it's a little bit difficult to understand. This is basically how, later on we're also going to go into more details. By having these two type of chain link, there are always trade-offs in terms of the performance of the blockchains, in terms of the validation of the way of validation of different blocks. And this I draw basically what happens for the chain link to be only the header of the blockchain. As I mentioned, if as a user A I want to send the money to user B, the first step is now I'm doing this transaction now. I actually commit this transaction behavior or transaction type into beacon chain as a transaction header only. And the second step I'm doing is the beacon chain will update, will inform the shard2 for the B on shard 2 is shard A is now sending you the money, and you should update the state of your account balance. So then the shard 2, B from shard 2 will acknowledge to the beacon chain, yes, I received the transaction already, and now the final step for the two-phase commit. This is not, again, not called two-phase commit anymore. This is more like an asynchronized commit. Then the final step is the beacon chain tells the shard, the A on shard 1, the B already received the transactions, right? So by doing that, we are able to make sure the transaction is valid and there's no double spend. But there's always issue, right? Because, for example, what if the shard B, the connection is gone? Or it's been hacked, I can't receive transaction anymore. So in general, the philosophy for that, I need this transaction to be atomic, which means either you are able to send me the money or I don't receive your money at all. And I think Andrew Michael or someone proposed this problem as a train hotel problem. We're gonna discuss briefly what does that mean again. So this, I give you an example during this transaction. And this is an example where the system had an issue, right? For example, now this is the main blockchain, canonical blockchain. And so by right, I should follow this pattern and adding block B into block A and A here. But now, for example, Alice is trying to transfer the money to Bob on shard 2 at block Y. So what if now the shard 1 got hacked, 51% attacked, then the shard 1 will actually become this blockchain. And by right, on the block A, I should deduct the money from Alice. But before I finish this step, the shard 1 got hacked. And actually, by doing this, right, Alice was able to do double spend because the transaction state is not receiving acknowledgement from the beacon chain. And the Alice balance is still the balance because I didn't really receive the acknowledgement from the shard 2, right? And that's where Alice got a double spend issue. Bob actually received the money. So there's another potential issues, like shard 2 also get hacked at the same time, where the blockchain become this. Well, if these two situations happen together, there's no double spend issue at all because as a Bob, I didn't receive the money. As Alice, I didn't send the transaction. So basically the train hotel problem is trying to say is like, as a business travelers, when I book a train to travel to the destination, I need to book a hotel. If I was not able to book the hotel or the train ticket, I shouldn't go. And this basically typically explains on this atomic transaction. And this need to be atomic. Any question for this example? Oh, good? Yeah, I think it should be easier to understand now after this. Yeah. So, so sharding in a nutshell, we have beacon chain. The beacon chain has an amount of validators pre-assigned. Normally, the validator for beacon chain is limited because, in general, when you do beacon chain, you use like Byzantine fault tolerance consensus, where they have maximum workload they can handle in terms of maximum amount of validators. And so when we run a shard chain, it's the same thing. We also run the same Byzantine fault tolerance consensus on the shard chain. So anytime the shard chain commit to the beacon chain, all these different shard chains also commit to the block if there's any update on each shard chain. And the beacon chain record all the information from different shard chain. So that as a beacon chain, we know whether the transactions on next block is valid, right? So, but at the same time, when the system run after Genesis block, the validator will be randomly or pre-randomly, depending on which kind of algorithm the system is using, assigned to the shard chain 2. The validator will be running from the validator pool, similarly to another shard chain. And remember back, there's on blockchain, on the database, there's a shard key. For blockchain sharding, we also got a shard key. In general, for example, Ethereum or some of the protocols too, in general, they are using the last few digits as the shard key to identify, for example, from 01 to 05. These kind of addresses belong to shard 1, and maybe from 6 to 10 belong to shard 2. That's how basically the users are sharded into different shard chains. So anytime there's new transaction happening and the shard chain generated on a new block on the shard chain, depend on the type of the chain link, right? They will commit the update to the beacon chain. And again, the same time, other shard will also update a new block to synchronize all the transactions on that shard chain. So, and finally, it comes to the beacon chain, where the beacon chain should also generate a new block after they validate all the transactions valid. So all this behavior, right, end of the day, even on the beacon chain, depend on the type of the transactions, whether it's whole block or whether it's only block headers, they will generate a Merkle tree for the validation purpose. So there's no secrets. So you think about the blockchain as a whole bunch of hashed Merkle tree, right? So there's a different protocols for different way to update the information on that. We will later on have 2 examples to show you how they are implementing that with different mechanisms. But in general, here we talk about any type of blockchain. If they are sharded blockchain, which is normally a layer 1, how the whole flow works. So definitely, so other than doing the Merkle tree validation, there's also a layer, as any of the blockchain works, there's a layer which is a Sybil resistance layer to check the Sybil resistance and make sure there's a no Sybil attack during the generation of new blocks. And as I mentioned, right, as a protocol, you can choose whether you should randomly assign the validators or pre-randomly or shuffle the validators, and how long do you want to shuffle the validators. That's fully depend on different protocol definition. But this is one nuance when you do like a sharded blockchain, right? And as I mentioned, for BFT, Byzantine fault tolerance consensus, normally the maximum validators is about 1,000. You cannot be handling more than that, because once you handle more than that, the system will be fully slowed down, or sometimes even got issues if you have too many validators. That actually become an issue because remember last week I talked about decentralization, right? If you only have 10,000 validators compared to like Ethereum blockchain, Bitcoin, you have so many validators, basically no limitation at all. Does this mean it's a little bit more centralized solution for sharded blockchain? Different people have a different idea. So I won't comment that much. This is the first example very interesting. So this actually is a first example I want to tell you. The blockchain, the protocol is called Zilliqa. Not sure, have you heard about this protocol before? Anyone? No? Zilliqa is based on the initial version of Elastico protocol. These whole bunch of solutions are invented by a bunch of PhD from NUS. And it's a Singapore-born blockchain. And I know the founders pretty well. It's called Xin Shu and Jiaqi. So now they are doing, the Zilliqa blockchain is still there. Has been running pretty well. Sometimes Singapore government was proud about this because they feel like, oh, this is a Singapore-born blockchain. Seems very encouraging after so many years of research. But the latest news, these two founders are doing two different things now. They are not at Zilliqa anymore. One is doing rollup now, rollup as a service, which is Jiaqi, the CTO of Zilliqa. The other one is doing, I think he's at Babylon now doing the Bitcoin layer 2. But I want to go through this one just to show you as a real protocol by using sharded blockchain, how do we balance the different parameters and finalize this final protocol as a mature product has been running in the market. They're still surviving, which is a good news. So these are the final choice for Zilliqa. So they use cross-link as an entire block. That's what they decided, which means anytime the transaction happening on the sharded chain, a new block generated, I upload all the block information into the beacon chain. And they also decided, other than use BFT, they using proof of work on the beacon chain. And they also decided to use a random algorithm called RANDAL, which is type of algorithm you can search about it. I won't go into more details about this. So basically, this is the one they decided to use, not VRF. So how the whole thing works, I want to walk you through. So the first step is I need to establish the identity for all the validators before the block start to generate the genesis block. So by using the POW, the validators, they are running this kind of POW algorithm on their validator node to establish the identity. So then they are using the RANDAL algorithm to randomly assign the shard, the validators into different shard. We call it shard committee. And then for anything happening within a block, which we call it intra-block committee. For example, the user A and user B are all in this block. I'm just doing transfer in between. They are using the PBFT as the consensus algorithm to generate a new block. Have you studied this algorithm, consensus algorithm before? Or BFT? Have you learned BFT before? Okay, cool. Yeah, it's just another version of BFT. No big deal. Then for the final consensus, it will be needed to broadcast to the beacon chain. And again, right, they decided the chaining type to be the entire block, and that's where they upload the whole entire block to beacon chain. So once the beacon chain receive that commit from different sharded blockchain, a new epoch will be generated on beacon chain. Again, right, this is only just for illustration purpose. They have multiple shards, definitely not only for 2 shards. The transaction, this we call it the transaction sharding only, which is commit to the entire block. Yeah. So do you have any question to this? Yeah. In a way, because it depends on which kind of, which part of the system you are seeing about Byzantine problems, right? So actually, from the architecture perspective, no matter it's here, because I'm using the PBFT to generate the Genesis block, to generate the block, and here I use the whole block information to generate a new block. And again, this is based on the POW to generate the block. I don't see any issues, but there's an issue for this because I actually later on can discuss about this, which means the beacon chain will be very heavy. Will definitely slow down the performance because I have all the information on beacon chain. Right. But from the Byzantine fault tolerance perspective, I don't see any issues, to be honest. I don't hear they had any attack, at least for the past 7 years. I think they established this about 7 years ago. Yeah. Yeah. So, so I want to pause here and let you think about, like, for what kind of computation the validators on the beacon chain do. Think back about this, the beacon chain and different shard. For the beacon chain here, what does the validator on the beacon chain do for Zilliqa? Any answer to this? Next time I should bring some small reward for you guys. For example, a radio t-shirt. Any question, an answer to this? Is it apparent? I hope you understand what I mentioned. The reason we pause here is really want to make sure you follow with me, understand what I said. Any answer? No? Shall I go back and repeat the whole thing again? Think about this, right? I'll give you an answer. So the validator will definitely need to validate the whole transactions from the whole entire block committed from the sharded chain, right? Where we need to validate the signature, the first step, on the sharded block, right? The signature, the block need to be correct, or else anyone can commit any block to the beacon chain. It shouldn't be the case. And also, we need to process the cross-shard transaction if there's any, right? If there's no cross-sharded transaction, that's fine, that's easier. But if there is, I remember we had the train, the hotel issue, the problems, right? We need to make sure get those information updated, right? And also we then aggregate, macroize all the raw blocks into the global state tree, right? This is basically what the validator in the beacon chain does. And if you run a validator for Zilliqa, you basically run a script and run this. Yeah. Okay. And so second question, I hope there's some answers there. Is there any validator on the beacon chain require more hardware resources than a sharded chain? I already told you an answer just now. Do you think they need more resources than beacon chain, than sharded chain? So think about, for shard chain, what kind of information they store? The whole block, right? The beacon chain, they aggregate all the blocks into the beacon chain. So the answer I already told you, as a beacon chain, they store all the raw blocks from all the shards. And require definitely more communications in terms of the communication bandwidth. Because imagine if there's a cross-shard communication, I have to update the shard chain each other. And the whole block, I need to communicate and make sure all the state are updated. And also the storage will be also multiple, because the beacon chain I have to store is basically double store all the data on the beacon chain. Yeah, but from the other hand, the computation won't be that much because it's only like double on the storage. So the calculation based on the Merkle tree is not that much from the computation perspective. So after this question, we'll have a pause, a rest. So for state validity and data availability, how Zilliqa guarantee those? We didn't talk about that, but do you have any idea? Because as a system, I need to make sure the state is validated, right? So that part I talk about it. But the data available, how do I make sure I have multiple replica or whatever you want to call data available when one of the data set is gone, right? So for the data availability, all the state are globally aggregated at a beacon chain level. So there shouldn't be any issue because when you store all the data on the beacon chain, it's not only one node, right? There are multiple nodes. So if there's any time there's any node on the beacon chain is down, so they are fine, right? There's no issue. But for the state validity, because they are using the BBFT at a shard chain level, so the level of the to ensure the level of the correctness for each shard block, if one shard is corrupted, right, the users could challenge the shard validators to provide the proof of state transaction at the beacon chain. And by right, as what you just asked just now, do they solve this issue? Because they are using the PBFT to do on the shard chain and also beacon chain with a POW, the malicious node or validators cannot hack the system due to how the has been designed systems. Yeah, so the next one is a near protocol. They are also a sharded solution in terms of the scaling of the blockchain layer 1. Compared to Zilliqa, they choose the cross-link type is block header only. And other than POW, they choose to use VRF, as we introduced already on the beacon chain. And again, they are using also VRF on the shard chain. Because they have been using these consensus algorithms So they also have parameters here, which is more like a threshold from the POS and transaction flow perspective. So where basically these thresholds tells you like you can check their web paper on what does this mean, but it basically explains to translate that message to the validators is like it will be easier for a low resources node because remember just now the Zilliqa one they need a pretty heavy loaded CPU and high-end CPUs to run the services. That's a sacrifice. But from the near protocol perspective, they decided to use VRF and a threshold for the POS and transaction flow to make sure the validator node can run lightly. That's their decision on the validator. And again, right, because they only transfer the crosslink as a block header, we call this is transaction and state sharding, or you can call it a data sharding. Yeah, so I think should be easy to understand, right? So very different to Zilliqa, they make the decision by having all the different algorithms in the different places. I won't go through like what I did for Zilliqa. It's the same process for the whole flow. But again, I got some questions for you guys. With this architecture, do you think they can add an infinite amount of shard into the system? Like just now, I mentioned for the beacon chain here, there's always multiple shard and the beacon chain, right? Do you think for this near protocol, they can add infinite shard into the protocol? The answer is actually no, because the beacon chain itself is still computational heavy. It's bounded by the node. The node need to maintain all the state, global state, and all those informations. Even though it's only block headers, you can't scale infinitely, right? Because you still have to store all these informations on the beacon chain. But there's an interesting thing about near protocol, which is there's a multiplicative effects for this type of architecture by using chain link as block header only. For each node on the beacon chain, if it's imagine the beacon chain the node, if it's 4 times faster on the beacon chain node, and also if it's 4 times faster on the shard chain node and also on the beacon chain node, the whole performance for the blockchain will be 16 times more powerful, which means they were able to handle more workload 6 times more on the workload perspective. So that's what we call it quadratic sharding, just because they choose to not upload the whole transaction into the beacon chain. That's where if you enhance the performance on 2 sides, the performance is square n in terms of 2n in terms of the performance for the 2n in terms of performance for the whole blockchain performance. Yeah. So I won't ask you this question because again, for near protocol and all the other protocol we just introduced, it's a different topic for data availability. So we will discuss in the second last section about scaling storage and the scaling consensus. We will talk about availability. I'll try to add in some of the latest technology companies are trying to come out. For example, Eigenlayer, Celestia, how do they do the data availability? It's a big topic. So today we won't talk about that. Yeah, but for near, they were able to handle the data availability properly. Yeah. So I think the last question will be much easier, like how to ensure state validity. Anyone has any? Just maybe run as a flow. How do you, as a near protocol, how do they really ensure the data validity? Anyone want to volunteer? Our plus at least one score for your class, for your final exams. That's a good incentive, I think. No one? Okay. So actually, this is not an easy answer. So to ensure the state validity, they come up with a whole flow. There are two approaches to ensure the state validity, because you can not only Merkle-rise the whole state tree. That's more from the consensus perspective to generate the node. But you need to validate that, right? Because there's maybe still opportunities, like people are trying to hack with the 51% hack. How can you make sure there's no issue at all, right? So definitely we need to validate that. So from the type of approach perspective, so one is called fisherman, or you can call it a fault-proof. So this approach will be used not only here, but also roll up later. So what does this mean? So the idea behind the fraud-proof or fisherman is we predefined challenge period time. So during the challenge period time elapsed, so anyone can question the computation integrity at a certain locality on a shard chain or on a beacon chain. Anyone can challenge it. So basically the way to challenge it is to provide evidence. Normally you run the whole Merkle tree and compare this current Merkle tree row state with the previous maybe -8 block to compare the validity of the state. So if there's no fraud proof can be generated, that means all the state is valid. So that's one approach to validate the state. Any question? Yeah. So again, right, the reason we go through all this is because the new idea is really challenging to have. So a lot of times people bring the old ideas into the new solutions, become part of the final solutions for different protocols. And again, right, this idea was brought to optimistic ROP. No difference. It may be different in a way like the near protocol is on layer 1. So they have to have the consensus algorithm to make sure the security is in place. For optimistic ROP, they basically derive the security from Ethereum. And the fraud proof is only happening when you withdraw the fund from layer 2. They are not doing all the block checking. But for near protocol, they check periodically for all the state, because no one guarantees the security other than them. Yeah, that's the only difference. But from the algorithm perspective, yeah, it's basically the same. Yeah, so the second approach, again, familiar. It's zero knowledge proof. I think both Justin and Prof. Guo, as far as I know, already explained the SNARK. So basically, they run polynomial functions from X to generate a Y, where by running this algorithm, they are able to get a zero knowledge proof, which is called pi. And by verifying the current pi with previous pi on the beacon chain and shard chain, they are able to validate the whole state is validated. Right, so it's the same thing, same idea, because end of the day, there are not so many new ideas. But we're gonna later on, I think not so many people will talk about Stark. I will talk about Stark during the ZQROP session. The Stark, briefly talk about this is like, other than using polynomial, they're using hash, which if you, definitely you should know from the efficiency perspective, hash function is much more efficient than polynomial. But the issue for Stark, later on we'll talk in detail, is the proof size is much bigger than Snark. Yeah. But Stark is definitely another way. But when near protocol was generated, Stark was not invented. That's why there's a way you can use Snark, but not Stark yet. Yep. So I go through a little bit more details on the fisherman side because this again we'll talk about once we finish this session. I won't need to talk about that during the optimistic wrap. The theory is the same. So this is a little bit messy. Let me walk you through. Imagine you have shard 1, and now there's a transaction happening on this state. So for when we run the challenge, right? So basically, imagine this state will be updated as a header, block header to beacon chain. And to challenge this transaction, I not only need to run the fraud proof on the shard, I also need to run the challenge on the beacon chain. For this example, we only talk about the beacon chain. So we need to when we challenge this one, we need to prove whether this transaction on this state is correct or not, right? So here we take an example like the challenge period time is about 8 blocks. So from this place I minus 8, we use this as a challenge period time. So when the state is updating and trying to generate a new block, so I need to know from the UTXO perspective, there's a UTXO I need to, from here, to generate a Merkle pass where I can get a transaction route by running this Merkle pass. So on this I plus block, again, right, I use the UTXO, the same UTXO, I run to validate the signature first to make sure the signature on the I plus 1 node is correct first. Then when before I try to generate this block, I need to run the Merkle pass from here to here. Because the beacon chain, I ran this one first, I got the block header, and I can get the block header state from here to here, right? So I basically compare this Merkle pass with this Merkle pass to see whether this one can be validated. If not validated, which means the fraud proof is valid, and the new block cannot be generated, the whole transaction will be rolled back. So that's the flow of fraud proof. Any question to this flow? Yeah, so this is the same flow later on when we discuss optimistic route for the fraud proof. So the next one is interesting. We will talk about ETH 2.0 sharding, finally. So for Ethereum, it's a little bit different because they already have a main chain running on top. To establish a beacon chain type of sharding architecture, they have to rely a lot on the main chain. Underneath, they have the beacon chain. The beacon chain, again, if you know already, they provide, you need to deposit in amount of ETH on the validator side, like 32 ETH, so that you are able to be the validator for beacon chain. And so the initial plan was like they want to support, if I remember correctly, it's about 100 plus shard for ETH 2.0. And again, right, no difference. The idea is the same. They will have a shard chain where I think they were designing to only upload the block headers to the beacon chain as the chain link. And definitely they need to run on top of the shard chain, and they need to run the ETH VM to execute the smart contract. So that's the architecture for ETH 2.0. It was long ago planning, but anyone know what's happening for ETH 2.0? Is it still happening? No one knows? You guys don't read the news. Ethereum had this like merge, surge, purge, and plurge. So that's the initial planning for end of the day. They want to achieve ETH 2.0 sharding. But interestingly, in the middle, layer 2 has been booming. And there are so many layer 2s. It seems in a way they solve the issues of scalability for Ethereum. And also in the middle, they realized from the current capacity for Ethereum, from the Ethereum perspective, to run a sharded blockchain on a multiple shard, it will be very intensive on the validator side, even though it's only block headers. So that's where they decided to leap away from ETH 2.0. If you guys heard about the term of 4844 EIP, so that's the name of that is pro-dense sharding. So they basically decided to, other than doing this kind of sharding, they decided to have a blob into the block. It's a little bit difficult to pronounce. The purpose for the blob is, so I don't have the slide for that. You can later on check on the pro-dense sharding on the EIP how they do that. So for the blob, they store the root state from the layer 2s. So later on for the layer 2s, we may touch a little bit on that too. So by doing that, right, they are able to offload the data from the consensus from the validator node calculation, because those data won't be part of the block to be calculated. And also that blob, in general, in theory, they only exist for 14 days. So after 14 days, those data will be purged or slashed. So, by doing that, right, they are able to reduce the gas cost 100 times for layer 2s. But for Ethereum, unfortunately, the performance, I guess, is not improved. But layer 2 got a lot of benefit from this decision. Any question? No? Actually, this decision make a lot of sense from the ecosystem perspective, but by doing that decision, we later on going to talk a lot about that. For layer 2, currently all the layer 2s are centralized. So that defeats the purpose of that decision. So I don't know how the industry is going to go, but so far all the layer 2s are centralized in a way. So from the specific perspective, I still want to run through this one because it's interesting in a way like even though Ethereum decided not to do ETH 2.0 sharding, but company like Harmony and some other blockchains actually implement this already in the last cycle, which is around 2016. So they were using the same thing, where on the consensus side, for Beacon chain they use VRF. On the sharded chain they use Casper. It's another type of FFT POS. It's another type of consensus. You can also call it friendly finality gadget for the FFT. So that's another type of consensus algorithm ETH 2.0 initially was designed for. So for, again, right, as I mentioned, the cross-link is a block header, not a whole blockchain, not a whole block. So because of that, we call this data sharding, transaction and state sharding, not transaction sharding. So the initial design was like, there's a term, they call it a proposer, but it's actually a validator. So they are pretty much a shard validator. But later on, if there's any terminology speaking like proposer, it's just a validator. So the validators are able to validate as an inspector to validate from the shard chain perspective and from B chain perspective to inspect the whole chain whether the state is valid or not. So they also have this terminology called notorious. So this again is just to sign on the checkpointed blocks. For when the new block generated, we have this idea called notorious to sign a new block. It's another layer of security. Think about it that way. Again, I won't discuss the DA for ETH 2.0 at this lecture, but we'll discuss in scaling storage during that time. We'll discuss that. Yeah, so that basically that's the end of the sharding. So the reason I want to talk about blockchain probability is because once you understand the state sharding, the logic for the blockchain interoperability is actually similar. Why? Because there are two typical solutions for interoperability in the early days, where at that time there are so many layer ones, and these two companies figure out I should come up a protocol allow the different layer ones to be able to communicate each other, to bridge the assets each other's. And for Cosmos, they have this idea called Cosmos Hub. So if you think about the state sharding, think about this is more like a beacon chain. And they also have a concept called zone. They have different zones. The zones are the similar ideas like a shard chain. But because the focus for them is more on the interoperability other than a single layer one sharded solution, they have designed in a way like each, no matter it's the hub or the zone, have the Tendermint consensus and a core to run the consensus and run the state machine. And all the different zones was also run the same consensus algorithm because each of them is independent, other than like sharded blockchain. They are in a one big blockchain. So in order for the two to communicate with each other, we have this concept called intra-block blockchain communication, called IBC, for the interoperability purpose. We'll discuss a little bit more on this part too. So similarly for Polkadot, we have this relay chain, which again is similar to beacon chain, as in the middle to relay all the different transactions to all the bridges between different, we call it the parachain. So the parachain, think about the parachain is more like a shard chain. So I list here, again, for you to easily understand, again, right, the beacon chain is Cosmos Hub and relay chain. The shard chain is similar to Cosmos Zone and the parachain for Polkadot. So all the shard runs for the state sharding, they run the BFT or POS. Different protocol have different consensus. But for Cosmos, they decided to use Tendermint consensus. Have you learned Tendermint before as a consensus? Okay, good. I'll later on talk about this briefly. It's an interesting protocol. And then they bridge to different parachain or zones. Zones bridge to different zones with Tendermint. The different zone will also run Tendermint. So for Polkadot, other than fix a consensus algorithm, they choose for you to choose whatever consensus you want to plug in. Some of the popular consensus Polkadot has been using are like hot stuff, BFT for sure, and there are fews has been implemented for that. For cross-shard transaction, the state sharding is called cross-shard transactions. The Cosmos is called inter-blockchain communication IBC, and the Polkadot is just using term as a cross-chain transaction. But I guess when initially these two companies invented this technology, they bought a lot of ideas from sharded chain. Today we'll talk briefly about Cosmos because I feel, that's not what I feel, that's what in the industry has been observed. Cosmos is more popular even now compared to Polkadot, even though Polkadot, the underneath SDK company using, which is called Substrate, has been using that to build different blockchains on layer 2s or layer 1s. But the majority of the companies has been using Cosmos to build their own layer 1. Anyone can give me any example, like which blockchain using Cosmos to build their own layer 1? Anyone? So in general, when they use Cosmos, there are some companies that they are trying to build a standalone blockchain for public to use, but a lot of time we call it a sovereignty layer 1 because in general they only use that for a single application. Because the reason they do that, the reason I talk about the Cosmos in this section is because, again, this is a computation scaling. So other than putting all the traffic like Ethereum into all the blocks, all the data into every blocks in a single blockchain, So now I have multiple blockchains. So that, in a way, scale horizontally from the blockchain perspective. That's where a lot of companies, when they want to scale, they use Cosmos to build their own blockchain. Some of the old examples are Terra. Have you heard about Terra? The foundation underneath is called Luna. Yes. Yeah, so actually Terra was using Cosmos to build their app chain. And the latest example, a company using Cosmos to build their blockchain is DYDX. So last lecture we talked about DYDX was using StarkEX to be the initial version of the scaling solutions. But later on they decided to use old technology to build their own layer 1. So now they already deploy, I think it should be version 5 for DYDX, where they use Cosmos to build their own layer 1 after so many years. Yeah. So briefly explain you guys on the Tendermint consensus. So just follow with me, right? So when the consensus for the Tendermint, again, right, it's a different version of Byzantine fault tolerance consensus algorithm, but they tweak a lot. So this consensus actually is invented by Cosmos team. So when a block started, sorry. They have this phase called propose. So now the tells all the validators I'm proposing this block as part of the consensus. So if it's valid block, they will generate a pre-vote block. So other than insert the block into the previous block, they actually wait for 2/3 of the validators to come back telling the consensus this provoke block is valid. So most of the Byzantine fault tolerance consensus algorithm, it's just 1/3 of the validators. More than 1/3 of validators can hack the system. But if 2/3 of the validators agree that the provoke block is valid, they can actually generate the next block. But again, right, to make sure this is safe enough, other than generate a final commit, they actually generate a pre-commit block. So this pre-commit block, again, the whole validator, all the validators will wait for the 2/3 of the validators coming back telling all the consensus node, all the node running the consensus, like this pre-commit block is valid. Only after that, they will commit and generate the new block and insert the new block into the previous block. So that's a Tendermint consensus. So why they are doing this? It's because other than the first one is more like a Bitcoin blockchain. A Bitcoin blockchain, there's a chance before the block, even after the block insert, you are still able to fork the block into different chain. But with these Tendermint consensus algorithm, they are able to deterministically generate the blocks in one go. And there's no way for any blockchain running on Cosmos to have a fork by running that 3 phases commit. So that's the direct benefit of that. So another benefit of running the Tendermint consensus algorithm is because they don't have a challenging time don't have a challenge period time, because the 100% the chain is valid after you commit. The processing time for finality is actually much faster. So with Tendermint and Cosmos, we are able to handle a workload about 10,000 transactions per second. With the Tendermint consensus actually contribute a lot to that. Definitely there's other reasons too. Another reason is actually the client. Other than like any other blockchain, you run the full, the client run a full block. They are able to, the Cosmos hub are able to run only the block headers. So because of that, they are able to calculate much faster, and because of that, so all the transaction time, they are able to generate the block, next block faster on the harp, and the finality is much faster compared to other blockchains. Any question? I know this is a little bit abstract. No? So because of this implementation, the Cosmos compared to Ethereum, the architecture is quite different. So on the left side, before the merge, the Ethereum has all the miners here as part of the block generation. For Cosmos, they run different applications, run different validators. And because they are able to to generate finality on a different application chain, they are able to get a consensus finalized much faster than the ones running on different miners. Even after the merge, the Ethereum run validators now together with miners. The Cosmos is still faster than Ethereum. So if we have time, we will actually later on run through some of the how you actually build your own blockchain with Cosmos, for example. But actually, the interesting for Cosmos is they actually have two different ways of programming the blockchain. What do I mean? So basically, the Cosmos is modular blockchain, where for all the client, they can run the client directly. You can modify the modular directly as part of the logic for the blockchain. Basically, it's run on Golang. So imagine you have a game or DEX program in Golang. You basically can execute the logic from the Cosmos directly, run that application logic, which is written in Golang. So that actually brings down a lot of cost from the developer learning curve perspective, because now you don't need to learn Solidity, for example. So this is actually part of the reasons Cosmos is that popular compared to Polkadot. Because Polkadot, compared to Cosmos, Polkadot design philosophy is very different. So, the actually Polkadot is designing in a way like, and the underneath is not modular, even though they call it modular. It's from the top-down approach. So the interface to the application is super easy to interact, but the underneath block, the underneath module is very difficult to change because there are many macro definitions and substrate. Do you have any of you have experience code on the Cosmos or substrate? No? Yeah, so if you are using the Polkadot substrate to build an application, super easy. Developers' feedback is very positive because I don't need to understand the things underneath in different modules. I can just code on top of the big modules. The interface is very developer friendly. But if you want to modify the blockchain, for example, into a layer one, like what Terra has been doing, it's super hard because the micro definition is huge. You don't know where to modify even when you do that. For Cosmos, on the other hand, you can modify any modular. I don't have the chart here. Later on, if we have time, in the last session, I can dive deeper a little bit on each modules. So each modules you can modify with Golang. And for example, the authentication, the signature, the consensus are different modules. The only drawback for Cosmos is, as I showed you previously, you can't modify the consensus layer because they fixed the consensus layer to be the Tendermint. But other than that, all the modules can be modified. I can run a script immediately after you modify. So the last but not least, I want to talk about briefly about the hubs and zones, how they make sure the different blockchains using Cosmos can communicate very easily. Before Cosmos was popular, if you want to cross different blockchains on layer one, it's very difficult, very insecure. Like what last lecture I explained you on the ruling chain, right? It's a side chain. We only had like 7 validators running, for example. You can hack it easily, only 6 validators. But for after Cosmos has been born, I would say anyone using Cosmos SDK for the two blockchain to communicate with each other is super easy. Where, for example, these two are two different blockchains on layer one. So anytime they need to commit the state on the global state to the harp know all the blockchains using Cosmos are validated, right? Because the same, I won't go through the detail, but the same logic compared to state sharding. So because of that, so in general, the Cosmos hub and zones are secure. Before that, for example, I have my team members used to code on Near protocol. So there are companies, the fork Near protocol have another blockchain. These two blockchains are different. They don't have any shared relay or hub to trust, right? So they don't know whether that blockchain has been hacked. With Cosmos hubs, this issue is resolved, right? So in order for the zone 1 and zone 2, or blockchain 1, blockchain 2, to transfer the assets, what they need to do is just lock up on zone 1 for the destinations and also the originators. And they definitely will keep track of that transactions on each zones for the hub. And so after that, right, the hub will generate a proof this transaction, and all the blocks on the global state on the zone 1 is validated. After that, we will actually send the transaction, like the money will send to the recipients on the zone 2. The reason is safe again is the hub take the initiative to make sure everyone is secure and safe. So again, right, it's very similar to the beacon chain and state sharding, shard chain from the security perspective. But it's very interesting, like we designed these and the industry actually doesn't follow because, for example, I know entrant was using the Cosmos, but they actually ran their own Cosmos hub as a BN chain. And then there's a BN smart chain, which is running EVM on top of Cosmos. And that become BN chain as a zone. So they were not using the Cosmos hub to guarantee the security. Actually, BN themselves guarantee the security. That defeat the whole purpose of the initial design of Cosmos hub and zone architecture. But as far as I know, I think DYDX was following this design principle. They were implementing DYDX was more like a zone, other than run the whole thing themselves. But so far, not so many companies follow that. Yeah. Any question to this? No? So actually, this is the last slide of this lecture. I want to make sure you understand the whole thing and the principle already. Basically, the state sharding is what we call horizontal sharding scaling for a layer 1 blockchain. And the initial purpose for all these modular architecture like Cosmos and Polkadot substrate is really for them to design interoperability across different layer 1 blockchains. So I think that's pretty much cover all the method to scale on layer 1. I don't think I missed anything. Yeah. Any other questions before we close this lecture? No? Yeah. Yep. Celestia. Yeah, that's a DA modular, yes. Yeah. Yeah. Yeah, so that I need to study further, but the initial design of Celestia was using Cosmos. But the current design, they actually changed multiple iterations already, become more like a DA used for layer 2. But the initial design was they were using Cosmos SDK. So they designed the whole thing based on Cosmos. But other than Celestia, I don't see other layer 2 has been using, or DA layer has been using Cosmos SDK for layer 2. There's company like Stackware, the community designed layer 2 or sequencer using Polkadot substrate. But because the design of the substrate, I think it took them 2 years to build the current version of the sequencer, which is called Madara. So that one is not production ready yet. So you can compare, right, how difficult it is to design on top of Cosmos compared to how difficult it is to design on top of substrate compared to Cosmos. So another reason, I already explained you the different approach they were using, right? The initial design for that, when they tell the developers we tell like the Cosmos is like Ruby on Rails for blockchain. And Polkadot is just a wholly newly designed architecture. It's super difficult to learn and modify the underneath architecture. So I think one more thing I forgot to mention is another way to program Cosmos is later on they introduced two modules. One is called EVM module. The other one is Cosmosum. It's more like a WASM kind of architecture for module for the module. So based on these two modules, you can actually write a smart contract on top, so that you can run anything on Ethereum. Now you can move to Cosmos based blockchain to run a smart contract. But the initial bunch of developers designed on top of Cosmos, they were not writing smart contract. They were modifying Cosmos modular directly as part of the transaction for Cosmos. Yeah. Any other questions? No? You understand all? I'll have at least 2 questions from this section on the exams. Because this is very important to understand the history of layer 1s and how people are using the layer 1s. And also for the layer 2, we're going to talk about in the next session, and the one after. A lot of companies also bought a lot of ideas from the layer 1 evolutions. No question? Yeah, if no more question, we'll close this lecture. Thank you so much, everyone.